Here we're going to be talking about gas laws. There's a bunch of gas laws that are important for historical reasons. There's Boyle's law, Charles' law, Avogadro's law, and then you can combine those three together to get the combined gas law. Some of you may be familiar with the ideal gas law, and these all do play into that, but we'll talk about that in a little bit. These are kind of the beginning gas laws, or maybe even sometimes called the simple gas laws. So for example, Boyle's law being a pressure-volume relationship, Charles' law being temperature-volume relationship, Avogadro's law being the amount of moles of gas to volume relationship, and then the combined gas law is just all of those factors together: pressure, temperature, amount, and volume all combined together. And that may look very similar to the ideal gas law, but it is slightly different. We'll get to the ideal gas law, but these are simple gas laws that are kind of we're going to build our way up to the ideal gas law if you're familiar with that. So let's start with Boyle's law. So this is a pressure-volume relationship. So this is showing that volume is inversely proportional to pressure. So if you were to increase the pressure on a gas, that would decrease the volume. And I don't think that that's very surprising when you think about gases and how those operate. So what this means is that if we are going to change the pressure or the volume of a gas and keep other factors the same, for example, keep the temperature the same and keep the amount of gas the same, number of moles of gas the same, you could set up a relationship like this, where you have the pressure times the volume equals the pressure times the volume. So the pressure times the volume in the first situation needs to equal the pressure times the volume in the second situation. So you could change the pressure and you would expect a volume change, or you could change the volume and expect a pressure change. So this is a pressure-volume relationship, Boyle's law. So this is what one of those might look like. So if you have some diver, they take a breath at the surface, they fill their lungs up to 5.82 liters with air. What volume would that air in this person's lungs occupy when they dive to a depth where the pressure is now 1.92 atmospheres? Assume that they're at the same temperature and that the pressure at the surface is exactly 1 atmosphere. Okay, so we're assuming constant temperature, and we're assuming that no gas is leaving or coming into their lungs when they're underwater, which I think is a fair assumption. So that means that we can use Boyle's law that because we have constant temperature and constant number of moles of gas in his lungs. So this is the setup. We have P1 V1 equals P2 V2. I would label all these variables. So the first situation is at the surface. So the first volume is 5.82 liters. The first pressure is 1 atmosphere. And then the only difference that we're getting is that the second pressure is 1.92 atmospheres. And the volume is what we're solving for. So we'll just solve for V2. Plug everything in. You can see atmospheres should cancel. And we will end with 3.03 liters of air in his lungs. So the volume decreased. That should make some sense. We increased the pressure, about doubled the pressure. So we should about have our volume. And that's what we see, right? Going from roughly 6 liters down to roughly 3 liters. So this, just quick mental math, seems to make some sense. All right, the second one is Charles' law. This is the temperature-volume relationship. And it's saying volume is proportional to temperature. An important note here is that you need to have temperature in kelvins for this to work out. And I think we have some familiarity with this. If you leave your bike tire in your hot car, for example, that gas will expand and you can blow out your tire, for example. So as you increase the temperature, you would expect an increase in the volume of a gas. And the opposite is also true. You can decrease the temperature and you would expect a decrease in the volume of that gas. So again, we can set up this is assuming that we are at constant pressure, and also assuming that you're not changing the number of moles of gas once again. So we can set up another sort of ratio here, where V1 over T1 equals V2 over T2. And again, yeah, it's at constant pressure and the number of moles of gas are not changing. So here you can see we do V1 over T1 equals V2 over T2. We just label our variables once again. We have a first situation versus our second. If anyone did this top example where you were getting 29.2 liters, an important note here again, remember, was that we cannot have degrees Celsius here. We need to put everything in terms of Kelvin, because the ratio of Kelvin to each other is what matters. This looks like you've doubled the temperature from 25 to 50, which is not true. In Kelvin, you're not even close to doubling your temperature. So you have to be careful of that. So yeah, again, we'll just plug this in, get about 15.8 liters. And in thinking about this, you're increasing the temperature, so you would expect the volume to increase. They are proportional to each other. And you see we did increase just a little bit, went from 14.6 to 15.8. We did not double the volume like we saw if you use degrees Celsius. Again, we need to make sure we're in Kelvin. All right, Avogadro's law. This is the amount of substance to volume relationship, and this is very straightforward. You would, as you increase the number of moles of gas, which is that scripted N, if you increase the number of moles of gas, you'd expect the volume to increase, and that makes a lot of sense. But in context, we often will talk about it in terms of the number of moles of gas in reactions, let's say. So we can set up a comparison between a reactant and a product, and just see that volumes, for example, in this reaction, volumes would decrease. So you have 4 moles of gas total on the reactant side, 3 from hydrogen and 1 from nitrogen, and you only have 2 moles of gas of ammonia on the product side. So you'd expect the volume to halve here, right? So you'd expect there to be a smaller volume in that final product than you do in the starting materials, which makes some sense. Again, we can set up a ratio V1 over N1 equals V2 over N2 in order for this to work out. And again, this is a simplistic situation. We're again assuming constant pressure and constant temperature. Those other variables we have to assume are being held constant. So this is what one of those might look like. If we combine 3 liters of NO and 1.5 liters of O2, they react according to this balanced equation. What volume of NO2 would be produced? Assume that the reactants and products are all the same temperature and pressure. Okay, so same temperature and pressure means that we are able to use Avogadro's law. We are only dealing with volume and number of moles, and so that's Avogadro's law. So that was V1 over N1 equals V2 over N2. And we have this constant, and so this is the setup. We have the balanced chemical equation, and if you take a look, you have 3 liters of NO and 1.5 liters of O2. You can't just add them together. It's not that you get 4.5 liters of product. You have to think about per mole. So this is 1.5 liters per mole, 1.5 liters per mole. So if this was also 1.5 liters per mole, you'd have 3 liters. So just quick mental math could figure that out for you, or you could prove that to yourself with actually plugging in the values. Sometimes, in this case, we can use the whole number ratios of moles. So N1, there are 3 moles on the reactant side, right? 2 from NO and 1 from O2. This is arbitrary. You could actually use real values here if you had another situation, but we have a balanced chemical equation, so we can just use the molar ratios. As long as that ratio is true, it's fine with whatever you put in here, because moles actually will cancel out, right? Okay, and then our product side, we have 2 moles total. So here we have 2 moles of product, and we don't know what volume 2 is, right? The volume of our product. So V2 equals V1 times N2 over N1, plug that in, and you'd get to 3 liters. Be really careful with these, because it'd be very easy to flip N1 and N2, for example, and that's true for all of these setups. Just be really explicit. Make sure that it makes sense at the very end. So I have fewer moles of product than I did to start with. So I would expect the volume to decrease. So that's what I should observe. I went from 4.5 liters of gas total down to 3 liters of gas, so that makes some sense. If I had inverted those moles of gas one way or the other, I would have observed the opposite effect. I would have seen a volume that was larger than the original volume. And that should have been a red flag to me to indicate that maybe I messed up my math somewhere. And that's a common issue, is just plugging in the wrong N1 versus N2, or T1 versus T2, or V1 versus V2. It's really easy to plug those in the wrong location. So that's why I would also label them pretty explicitly, like over here on the left-hand side, with a key that is very explicitly pointing out what is what. I found that to be quite helpful. All right, we can also combine these gas laws together. So you can have a pressure, temperature, amount, and volume relationship. And this is just jamming together what we had dealt with, all of those simple gas laws, so to speak. So here, P1 V1 over N1 T1 should equal P2 V2 over N2 T2. And this is actually, you could just start right here for all of the gas laws. If anything is held constant, those would cancel out. So if volume doesn't change, V1 would equal V2, so those could cancel, and you'd have a new relationship. Or pressure, right? Pressure didn't change, so P1 would equal P2, so those would cancel. Or commonly, for a fixed amount of gas, N1 equals N2, those would cancel. So you can always kind of create your own setup in doing this, and this is a way that you will get to all of the different all those different simple laws. All those simple laws just had 2 of the 4 variables that were fixed, and that's how you could get to those relations there. So we could try one of those. Let's say a child releases a 6.25 liter helium balloon in the parking lot of an amusement park where the temperature is 28.50 degrees Celsius and the air pressure is 757.2 millimeters of mercury. So remember, 760 millimeters of mercury is 1 atmosphere. So that, that makes sense. That's about 1 atmosphere. What will the volume of the balloon be when it has risen to an altitude where the temperature is now negative 34.35 degrees Celsius and the air pressure is now 366.4 millimeters of mercury? So this is a little more challenging because we're having 2 different variables that we know are changing, right? So we have a pressure change going from 757.2 millimeters of mercury to 366.4 millimeters of mercury. And we also have a temperature change, 28.5 degrees Celsius to negative 34.35 degrees Celsius. And we want to see the effect on the volume. And again, we're assuming that the number of moles of gas in a balloon are staying the same, which I think is a fair assumption. So we're going to use the combined gas law. So this is the combined gas law. As kind of a spoiler, this equals a constant, this PV over NT, and that's the gas constant, which is equal to R. We'll talk about that in the near future, but you could be aware of that if you've seen this before. So we have a fixed amount of gas, N1 equals N2, so the N1 and N2 will cancel, so we can have this relationship here. Again, I'm labeling everything. So P1 is at ground level. That was the roughly 1 atmosphere. P2 was the lower pressure. Our volume initial was 6.25 liters for the balloon. We're trying to solve for V2. And again, our temperatures are changing quite a bit here. But we need to put our temperature in Kelvin. So remember, that was degrees Celsius plus 273.15 Kelvin. So you can get your temperatures in Kelvin. You just solve this equation for V2 and plug in everything. And V2, you get 10.2 liters. So we actually see an increase in volume. The reason this is important is because mental math here would have been challenging because we're decreasing the pressure, which should have indicated an increase in volume, which is what we saw, an increase in volume. But we were also decreasing temperature, which that should have decreased the volume. So these are kind of competing features to this problem. And it turns out that the pressure situation 1, you're decreasing the temperature, but not that much. And here you're dramatically decreasing the pressure. So this pressure thing ended up being more important, where that volume actually ends up increasing, which I don't know what you would have maybe guessed from a situation like that. But yeah, so this is a way that we can deal with multiple factors at any time. And again, in fact, you can always start with this combined gas law, and you are able to then derive those simpler gas laws just based on knowing what is being kept constant at any given time.